So what you can see in my screen, I mean, just let me know. Okay. So yeah, so we are discussing finite difference method. Okay, and this so right. So let me start with the finite difference method. So this particular finite difference method, right? So that is actually it is based on Taylor series expansion, right? So now the question comes around that why we want to study this any of the discretization scheme. Okay, so in order to understand that, let us try to recall the second order partial differential equation. So I can you can cast any of your fluid flow and heat transfer equation using one of the standard formula which I am writing over here. So on the left hand side, or you can see your first term is rate of accumulation, which can be written as del by del t into rho phi. Okay, then you have a advection term that is normally written as rho v phi, and then on the right hand side you have a diffusion term which can be written as rho gamma and del phi, and plus then you have a source term. Okay, so this is a you can say generalize your governing equation. So you can cast any of your heat transfer or fluid flow problem using this particular equation. Now if you carefully see this equation, then you have a various differential terms, right? For example, if you see the first term, then this is a first order derivative term with respect to time. And here also you have a first order derivative with respect to space, right? But if you see this particular term that is equal to diffusion term, then here you have a second order differential term, right? And then you have a source term that can be of any function. Okay, so in nutshell you can say that in your governing equation you will come across many such differential term that can be of that can be expressed as a del phi by del x, or you can say del phi by del y, right? Or del phi by del t when you are working with transient kind of phenomena. Then you can also have a del phi by del z if you are working with both x, y, and z coordinate. Okay, so these terms are first order derivative. Then you can also have a second order derivatives like del square phi by del x square, then del square phi by del y square. Then you can also have a mixed derivatives like del square phi by del x del y, right? So if you come across any such terms, then how you can discretize in this finite difference method. So that is what something I will explain in this particular part. And not only that, we will also understand how you can gain or how you can improve the accuracy of all these terms, right, by introducing more and more neighboring point. Okay, so that is the whole idea of this particular session. And I will also explain some of the basics, our equation, that is classification of partial differential equation, then why we need to understand the characteristics of partial differential equation. So that is also I'll try to cover, right? So yeah, so let us start with simple philosophy of finite difference method, right? So the ultimate aim of this finite difference method is to express these derivatives that is we have discussed. I mean, that is not only this term. Okay, you can also have del cube phi by del x cube, or any higher order term you can have in your equations. Okay, so if you want to express all these derivatives in terms of suitable algebraic differences, right, using Taylor series expansion, then this finite difference method comes into the picture. So one of the basic terminology or basic tool that you have to use is the Taylor series expansion. Okay, so let's suppose I'm talking about one dimensional domain. Okay, so this is, let's suppose, one dimensional domain, and this is one of its boundary, which is left and right boundary. And let's suppose this is a point, this is a coordinate x, because this is a one dimensional domain, so we'll be focusing only on x coordinate system. And let's suppose so according to discretization scheme, we have to divide the whole domain into number of grid points. Okay, so let's suppose these are some of the grid points, and let's suppose at a distance of x, at a distance of x, uh, right, you have a one grid point, and let us call this grid point as a node number I. Okay, because this is a standard terminology which we are going to use, and that terminology we will replicate in our coding. Okay, so the subsequent node on the right hand side is obviously I plus 1, and then you can also have I plus 2, right? And on the left hand side you have a I minus 1, I minus 2. Okay, and let's suppose the distance between I and I plus 1 is delta x. Okay, and for the sake of simplicity, we will assume that this delta x is actually uniform. Okay, so we will assume uniform grid size. Right. Now, what is the next target, or what is our next aim? So we want to express any function which is at this particular point. So let's suppose this is a x. So obviously the position of this particular point is x plus delta x, right? Because the distance between I and I plus 1 is delta x. So we want to express any function at x plus delta x in terms of this particular function which is at f of x. Okay, so and this function can be your temperature or velocity, right, or pressure. Okay, so in order to do that, you can recall the Taylor series expansion. Okay, so this is the equation of Taylor series expansion where you can write in forward marching you can say that f of x plus delta x, that is equal to f of x plus f prime x into delta x plus f double prime x into delta x square by 2 factorial. Then you can also have f triple prime x delta x cube by 3 factorial and so on, right? So that is called higher order terms. Okay, so now for in this particular problem, let us start with one of the starting point that we are interested to find this first order derivative. Okay, so this is our first order derivative. So we want to express this d phi by dx, or you can say del phi by del x term. So this is the first one dimensional domain. So your del phi by del x is nothing but d phi by dx, right? This is actually your ODE. Okay, so you want to express this first order derivative, which is nothing but d phi by dx. Right? Similarly, your f double prime x is nothing but d square phi by dx square, and so on. Right? So we are interested to express this particular term d phi by dx in terms of finite difference between given function. Okay. So what we can do, we can take all the variable on the left hand side and express f prime x. So your final expression can be f prime x, or you can say d phi by dx is equal to f of x plus delta x minus f of x divided by delta x, because this delta x is actually in the multiplication term, so that comes into the denominator part. And then we are also bringing all the remaining terms, so I'll take this minus sign, then f double prime x delta x square by 2 factorial. Then there are higher order terms, right? That is not I'm writing. So let's suppose we are actually neglecting this particular term. This is called leading order term, or you can say higher order term. So short form is HOT. Okay. So if you are neglecting these higher order terms, then your final expression of d phi by dx can be expressed with this expression. Okay. Now if you see, okay, there is a one small mistake that here you won't have delta x square, right? Because we are actually dividing this particular term with delta x also, right? So here delta x comes into the picture. So finally you will left with only delta x. So now if you see the order of this particular delta x, then you would notice that this is actually delta x is 2. Okay. So the term which you are neglecting, that decides the order of accuracy. Okay. So order of accuracy for this particular formulation, you can say that its accuracy is order of delta x. Okay. So you can say that this is the first order accurate. Now, if you want to improve accuracy, you can actually try to decrease this delta x, right? If you try to decrease delta x, that means you are considering more and more number of nodes. Okay, that means you are actually increasing the computational cost or computational time, right? Other way of improving, this the accuracy is you derived an expression where order of accuracy is delta x square. Okay, that I will explain later. But since we started this particular, explanation, so let us complete that part. So we have derived this d phi by dx by using this forward, differencing scheme. But there are certain expression where you can also express f of x minus delta x, right? Because this particular term is x, so the node, this particular node is situated at f of x minus delta x. Okay, so if you want to express f of x minus delta x as a function of f of x, then you can recall the Taylor series of expansion with backward, marching, right? So your equation would be f of x minus delta x, that is equal to f of x. Then you have an alternate sign, so you will have a delta x, then f prime x, then plus delta x square by 2 factorials, then f double prime x. Then I am just writing another term, that is delta x cube by 3 factorials, and f triple prime x, and so on. Okay, so here also we are following the same philosophy, that we are interested to express f prime x as a finite difference between all these function, right? So if you rearrange this particular term, then you will end up with this expression, that f prime x, that is equal to f of x. So what we are doing, we are actually taking this particular term to the left hand side and this particular term to the right hand side. Okay, so you will come this particular formulation, that is f of x minus f of x minus delta x divided by delta x, because this delta x is already there. Okay, just let me know if I'm having some lag. Okay, yeah. Okay, so this is the expression, but obviously you also have some higher order term that is written over here. Okay, and some other terms. So here also, if you try, you neglect the higher order term which are shown over here. So if you neglect this higher order term, then here also I made the same mistake, that here you will left with only delta x, right? Because here also in the denominator you have a delta x, so delta x square divided by delta x, so you will left with only delta x term. So here also, based on, if you neglect this particular terms, then you will left with only this formulation, and order of accuracy of this particular formulation depends on order of this particular delta x, right? And we know that the order of delta x is actually 1, so you can say that order of accuracy is delta x, right? So the problem which I mentioned you, is only delta x, or you can say first order accurate, right? Now if you want to improve the accuracy of this formulation, then you have to have some formulation which has a order of accuracy more than delta x, or more than 1. Okay, so for that, what you can do, you can recall these two equation. Which two equations? This equation, let me call this equation as equation number 1, and this one as equation number 2. Now I want to have this particular term, right? F prime x is something which I am interested. So I can see that if I add equation 1 and equation 2, then this particular term and this term will be cancelled out. Okay, but that is not I'm interested. Okay, so what I'll do, I will subtract equation 2 from equation 1, so that this term will be cancelled out. I'm skipping this part, and I'm writing over here. Okay, so what I'm doing, I'm subtracting equation 2 from equation 1. Okay, so with this expression, what I'll do, what I'll get, so on the left hand side I have a f of x plus delta x. Here on the left hand side I have a f of x minus delta x. Okay, so with that I'll get f of x plus delta x minus f of x minus delta x, and on the right hand side I can see that this particular term and this particular term will be cancelled out, right? Because we are actually separating this equation. Whereas the second term, that these two terms will be add up. Okay, so I'll get, okay, and similarly if I see the next term, so here this particular term is positive, and because we are separating this particular term, so these two terms will be cancelled out, right? But when it comes to the fourth term, these two terms will be added, right? So I can write this equation as 2 times delta x cube by 3 factorials and f triple prime x. Okay, and then obviously you will have some higher order term which we are not considering for the time being. Now we are interested to express f prime x, so let us rearrange this particular equation. Okay, so finally you will get f prime x, that is equal to f of x plus delta x, then f of x minus delta x divided by 2 delta x plus 2. Here you have a delta x cube, but we are also dividing this with 2 delta x. Okay, so at the end you won't have this 2, as well as you will left with delta x square term. So you have this delta x square by 3 factorial, and obviously this is supported by f triple prime x and plus higher order term. Here also we'll do the same philosophy, that let us neglect the higher order term. Okay, so this is your final formulation of first order derivative, that is d phi by dx, or you can say f prime x. Now if I want to express, or I want to check the order of accuracy of this particular formulation, then I have to see the order of delta x from the neglected term, or you can say the first neglected term. Okay, so from this expression I can say that the order of accuracy of this expression is delta x square, right? That means it is more accurate as compared to the previous two formulation. Okay, so now if I express all three formulation on a pictorial view, then I can first take this domain. This is my node I, so this is my node I plus 1, this is my node I minus 1. Okay, and I want to express d phi by dx at this particular node I, right? This is nothing but our f prime x. Okay, so we are actually working out to define d phi by dx in terms of finite difference, uh, between neighboring nodes. So if I recall my first formulation, then first formulation was something like this. So d phi by dx at I was actually, or you can say at x, is f of x plus delta x minus f of x divided by delta x. Okay, this was the first equation which we derived in our discussion. Okay, so when I write my d phi by dx in this particular formulation, that means I am considering these two nodes I and I plus 1. Okay, if I recall my second expression, then it was f of x minus f of x minus delta x divided by delta x. So while writing this expression, I was actually referring to these two nodes I and I minus 1. Okay, and if I rewrite the third formulation which I just derived, then that was actually f of x plus delta x minus f of x minus delta x divided by 2 delta x. Okay, that means I am actually referring these two nodes, these nodes and these nodes. Okay, that is I plus 1 and I minus 1. And again, if I recall the order of accuracy of each of this formulation, then I know that order of accuracy of this formulation is first order, that is delta x. Here also you have a first order accurate, but in this particular case you have a second order accurate. Okay, so so I mean this is more accurate as compared to the previous one. Okay, now based on this particular analysis, you can name this formulation. Okay, so this first formulation is called forward difference formulation. Forward difference formulation, because we are at point x, so this particular point is actually x. This is at x plus delta x, and this is at x minus delta x. Okay, so we are at point x and we are moving at x plus delta x, or we are actually taking the point which is available in the forward direction. So that's why this particular equation is called forward difference formulation. In the similar manner, this particular formulation is called backward difference formulation, right? Because we are at x and we are taking the help of node which is available at x minus delta x. And if I talk about this final formulation, then this is called central difference formulation, right? Because our point x lies in a central position between I plus 1 and I minus 1. So that's why this particular formulation is called central difference formulation. Okay. So far, if I summarize what we have derived so far, so we have derived three expression of d phi by dx. Okay, and the first two expression is of first order accurate, and the third one is second order accurate. And with this formulation, I can say that the last one is more accurate as compared to the first two expression. Okay, now is there any other way to get more order accurate expression, right? So that is the main question. Okay, so can we have a formulation with order of accuracy of delta x cube or delta x to the power 4, right? Can we derive this expression? Or this is first question, so this is we have written for d phi by dx. Okay, then can we derive similar expression for higher order derivatives like d square phi by dx square or d cube phi by dx cube? This is second question. Then can we have also separate expression with forward difference approximation, then backward difference approximation, then central difference approximation, right? So this is the third question. Can we derive similar kind of expression? Because if you see this forward difference approximation, then we are actually talking about only these two terms, this term and this term. So this particular approach is called one-sided approach, because we are not taking point on both the side. We are taking one point and another immediate point only from one side. Okay, so this forward difference approximation is called one-sided approach. Similarly, if I talk about this backward approximation, then in that case I am taking these two nodes. So this is also one kind of one-sided approach. Okay, but if I talk about central difference approximation, then I am taking this node and this node. So these two nodes are on the both side of this node I. Okay, so this is called two-sided approach. Okay, so sometimes I will also refer instead of forward and backward, I would write simply as a one-sided approach. So you need to understand that I am talking about either forward or backward. But when I am talking about two-sided approach, then I am actually talking about central difference approximation. Okay, so these are some of the questions which we try to answer during this particular session. Okay, but before we do that, I mean, why we need to have more accurate approximation, right? So in order to understand that, let us take a simple example of our daily life, right? For example, if you are interested to purchase mobile phone nowadays, people purchase from uh, our online digital platform like right? For example, you visit Amazon or Flipkart, right? But you are not blindly actually purchasing. Okay, for example, if you go to some shop, then you actually first try to visit one shop, then you try to see the another shop, right? For example, in Gujarat, normally the Skroma and Vijay sales are more famous, so people visit that place and they check what are the prices they are offering. Okay, but based on these two shops, you cannot decide, or if even if you decide, then you might be in a confusion whether you got the correct deal or not. So it's better to look after more number of shops, that you then you can have a confidence. Even if you visit the shop, then you check the online platform whether they are offering any good deal or not, right? So if you refer more and more this kind of points or notes, then you get some more accurate results. So similar philosophy we are also apply over here, that you don't define your function based on only one or two neighboring node, but you try to involve more and more number of nodes, so that you can get a more accurate formulation or more accurate values. Okay, so that is a simple analogy I can explain in terms of why order of accuracy is very very important. Okay, Let Okay. So far we have discussed only these three schemes, that is for d5 by dx. Okay, so this formulation is also for d5 by dx. This is also for d5 by dx, and this third formulation is also for d5 by dx. So one thing is for sure that this formulation is only applicable for first order derivatives. Okay. Now let's suppose you are interested to express or derive another formulation for d square phi by dx, right? For example, if you are interested to solve, let's suppose two-dimensional heat conduction problem, then you can have this particular term, that is d square t by dx square plus, it's not d actually, it's del, right? So del square t by del y square, it is equal to 0, right? So here you would come across second order derivative terms. Okay, so we are not going to separately define terminology for del square t by dx square and del square t by del y square, but let us focus only on one of the second order derivative. Let's suppose it is a del square t by del x square, or in that particular formulation it is like f double prime x. Okay, so how would you get the formulation of f double prime x? So in order to get that expression, you can again revisit the same two equation which we have written. So let us go back to this equation. So yeah, so these are the two equation. Okay, so let me remove certain things so that we can have a some space to explain. Okay. Okay, so I'm talking about these two equations which we have written. So one is for f of x plus delta x, and another one is f of x minus delta x. And now here at this particular time we are interested in this particular function, that is f double prime x. Again, I am facing some issue. Let me. Okay, so I hope now it worked fine. Yeah. So let me repeat this thing. Okay, so these two equations which we are talking about, but now double prime x. What is the second equation? Yeah, this is the first equation and this is the second equation. Now if I subtract equation 2 and equation 1, then I will get rid of f double prime x, but I want to retain these two function. Okay, so what I'll do, I'll add these two equation, right? So if I perform equation 1 plus equation 2, then I will, on the left hand side, I will add this equation or this term with this term. Then these two terms will be added, so I'll be having 2 times f of x, and this term will be cancelled out because of opposite sign, and these two terms will be added, so you'll be having 2 times f double prime x, but we also know that here we have a 2 factorials, right? So that 2 and 2 will be cancelled out. Okay, so with this understanding, I will write the expression over here, right? So if I add equation 1 and equation 2, so on the left hand side obviously I'll have a f of x plus delta x plus f of x minus delta x. Okay, and on the right hand side I can write as a 2 times f of x, right? And then 2 times f double prime x into delta x square by 2 factorial, but as I mentioned you that this 2 and this 2 will be cancelled out. Okay, so you have this term, and there are certain higher order terms which I am okay, let me write that particular term. Okay, because we will be needed that particular part, because ultimately we want to write what is the order of accuracy of this formulation, right? So for that, I think you will be having this particular term. So h, let us revisit that equation so that we don't have any confusion. Okay, so here if again I see uh, this is positive. Okay, but where is the other equation? Yeah, sorry. So this is actually negative. Okay, and this is positive. So these two terms will be cancelled out. So you will have delta x to the power 4, right? Am I correct? Are you with me? Okay, so anyway, so where is that term? Yeah. So here you will be having 2 times f of x, then f prime x will be cancelled out. Then f double prime x will be there. Then f triple prime x will be cancelled out. Then you will be having f4 prime x. Right, so h to the power 4 by 4 factorial and f4 prime x, right? Sorry, it's not h but it is delta x. So delta x to the power 4 by 4 factorials into f4 prime x plus higher order term. Okay, so here we are interested in f double prime x, right? So we will take, I mean, keep this particular term as it is, and we will take other terms on the left hand side. So my final equation will be something like this. So f double prime x will be equal to f of x plus delta x, which is nothing but this particular term. Okay, then I will take this particular term to the left hand side, so it becomes minus 2 times f of x. Okay, now it's actually, let me shift this particular equation. Okay, then I will write this equation. So I mean this term, that is f of x minus delta x. Okay, and that particular term will be divided by delta x square. Where is delta x square? This delta x square will be comes into the denominator part. Okay, and then I'll write the remaining equation. So that is actually f4 prime x, then delta x to the power 4 over 4 factorial, and this will also be divided by delta x square. Okay, so this delta x square and this delta x square will be cancelled out, so you will left with only delta x square. Okay, and then you will have some other terms. So here also we'll perform the same analogy, that let us keep this particular terms and neglect the higher order term. Okay, so this is your one of the formulation of d square phi by dx square, and you can see that order of accuracy of this particular formulation is delta x square. Okay, which is your second order equation, right? So now you have only one expression for d square phi by dx square. Can we have another expression which is of the order of delta x or not, right? So that is what we will look in the upcoming time. But what is the problem now, right? So now if you recall this particular expression, okay, then you need how many nodes? Let us try to understand that particular aspect. Okay, so let's suppose this is your one dimensional domain and this is your node x. This is a node which is at x plus delta x, and this is a node at x minus delta x. Now if I want to derive or write this particular expression, that is nothing but d square phi by dx square at I, right? So this can be expressed as I plus 1 and I minus 1. So for this formulation, I need three nodes. Okay, one is at x plus delta x, which is nothing but this node. One is at f of x, and another one is x minus delta x. Okay, so then only I can write this expression, and I can get an accuracy which is of the order of 2, right? But for example, you are working with one of the problem, right? For example, you talk about Cote flow, right, where your one of the boundary is wall, and at the top surface something is moving with a velocity of u, right? Then if you want to get the velocity distribution, or let's suppose this is your domain of interest, then what you will do, you will first you divide this domain into number of grid points. Okay, so let's suppose this is grid number boundary grids, then you have some intermediate grids, and this is again boundary grids, right? So you have two boundary grids, and again here also you have a boundary grids, whereas these grids are actually intermediate, or you can say domain grid. Now if I want to express this d square phi by dx square, okay, with obviously second order accuracy which we have discussed so far, then I don't have any issue, because for example if I talk about this particular node, then I need to have a two neighboring node. Okay, for example if you see here, you need two neighboring node for this particular x. So here also if you want to have two neighboring node, then these are available actually. Similarly, if I talk about this particular node, then I also have a two neighboring node for this node. Okay, so I can use the expression which I just derived. But when it comes to this boundary node, okay, when it comes to this boundary node, then I don't have any neighboring node on the upper side. Okay. Similarly, if I talk about this particular term, then I don't have any boundary node on the lower side. Okay. Then how can I get those information, right? For example, let me talk about first order derivative, right, that we have derived. So we have derived three expression. One is with forward difference approximation, another one is with backward difference approximation, and last one is with central difference approximation. We also know that order of accuracy of this particular approximation is 1, or you can say delta x. Then order of accuracy of this approximation is also delta x. Okay, and order of accuracy of this particular approximation is also delta x. Expression is delta x square. Here, right. So if I talk about this particular term, I want to retain second order accuracy throughout the domain. Okay. For example, for intermediate domain, I can use this central difference scheme, right? Because if you recall central difference scheme, it was something like this. You have this particular node I, or you can say x, then you have x plus delta x, and you have x minus delta x. And you want to express d phi by dx at node x, or you can say I. Then you can write f of x plus delta x minus f of x minus delta x divided by 2 delta x. So this is your second order accurate central difference scheme, right? That is we derived, right? So now what is, if you want to retain higher order accuracy, or you can say second order accuracy with this derivative, then is it possible to apply this scheme for boundary node? No, right? Because we need to have a one node on the upper side and one node on the lower side, right? For example, you are interested to calculate, shear stress, that is tau. Then tau is actually mu into du by dy, mu into du by dy. Okay, and let's suppose you are talking about at y equal to 0, that is nothing but bottom boundary. So here you can easily use forward difference approximation to get du by dy. But problem you will face is that this is first order accurate. If you want to use second order accurate central difference scheme, then you don't have any node on the lower side, so you cannot use that particular scheme. So how will you get second order accuracy, right? And same logic is also applicable for top boundary node. Here also, if you want to calculate shear stress, that is mu into du by dy, then here you can use this backward difference approximation because this node is available. But with backward difference approximation, you have only accuracy which is first order accurate, right? Here also you cannot use central difference approximation because no node is available on the top side. So will it be possible to go with backward difference approximation, add other terms and get second order accuracy? Okay. So that is what we are going to derive. Okay. So I hope the purpose of having higher order accuracy is clear, right? So we can use central difference approximation for the intermediate domain and get second order accuracy. But when it comes to boundary node, we cannot use central difference approximation because sufficient nodes are not available to us. Okay, in that case, we need to have some other formulation so that we can get higher order accuracy, and or you can say you can maintain the second order accuracy. Okay, so I'll start deriving those kind of expression. But before doing that, let us try to understand what we have covered so far. in terms of one kind of one dimensional steady state heat conduction problem. Okay, and then I'll explain how you can derive higher order accurate scheme. Okay. Okay, so let's suppose this is a problem, one dimensional heat conduction problem. Okay, and let's suppose this is a boundary at x equal to 0, this is a boundary at x equal to L, and let's suppose we are implementing heat flux that is equal to 0, or you can say adiabatic boundary condition on the left hand wall, and the right hand wall is actually maintained at some constant temperature that is equal to TL. Right. Now, according to finite difference method, what we will do, we will actually divide the whole domain into finite number, or you can say discrete grid points. Okay, so let's suppose we are dividing this, uh, domain into finite number of grid points, and let's suppose we are having 5 grid points, including, grids at the boundary. Okay, so this is 1, 2, 3, 4, and this is grid number 5. Okay, and let's suppose we have a uniform grid spacing that is delta x everywhere. Okay, now first of all you need to have a knowledge of governing equation. So for this particular problem, our governing equation is d by dx into k dt by dx, that is equal to 0. So this is our governing equation for one dimensional steady state heat conduction problem. Okay, so I'm not talking about transient phenomena as of now. Okay, now if you consider that thermal conductivity is constant throughout the domain, then you can take out this particular term, that is thermal conductivity, and your equation is like k into d square t by dx square, that is equal to 0. So this is nothing but your second order derivative, right? And for that we have already derived an expression based on central difference scheme, and order of accuracy of that particular scheme is delta x square. Okay, so order of accuracy is delta x square, or you can say second order accurate is the appropriate word. Okay, so if you recall what was the expression for d square t by dx square, then that expression was actually f of x plus delta x minus 2 times f of x plus f of x minus delta x divided by delta x square, and plus higher order term which we have neglected. Okay, so what you need 3 nodes. Okay, that means the nodes which is at I or x, then subsequent node on the right hand side which is at x plus delta x, and subsequent node on the left hand side which is at x minus delta x. Okay, and we are talking about heat conduction problem, so our function is nothing but temperature. Okay, and in terms of node number, you can say we are talking about t at I, then t at I plus 1, and t at I minus 1. Okay, so I can rewrite this expression as d square t by dx square, that is equal to t of I plus 1 minus 2 times t of I plus t of I minus 1 divided by delta x square. Okay, and that is second order accurate. Now, this particular formulation is applicable only for the intermediate node. Applicable only for intermediate node. Right? The question is why it is applicable to intermediate node, because you need to have a two neighboring nodes in order to apply your d square t by dx square at any particular I. Okay. So if you talk about this domain, right, so for this particular node I have two intermediate or two neighboring nodes, right? Similarly for node number 3 I have neighboring node which are nothing but 2 and 4. Similarly I can have neighboring node for node number 4, but when I it comes to node number 5, I have only one node on the left hand side, there is no node on the right hand side. Okay, and similarly if I talk about this particular node, that is node number 1, then there is only one node on the right hand side, there is no node on the left hand side. Okay, so here you can we know that this q is nothing but k into dt by dx, right? Or you can say simply say that this is nothing but dt by dx. Okay, and q is equal to 0, that means obviously dt by dx, that is equal to 0. Now this dt by dx, this is our first order differential term, right? And for that we have derived three expressions: forward difference approximation, then backward difference approximation, and central difference approximation. And again, if you recall the order of accuracy, this is only first order accurate, delta x. Okay, I am so I'll just write in a simple way that this is first order accurate, this is also first order accurate, and this is second order accurate. Okay. Now for node number 2, 3, and 4, we are using this equation, which is second order accurate. Okay, that is a good part, that we are able to write expression which is second order accurate. But when it comes to this particular node, node number 1, we cannot use central difference approximation because we don't have any node on the left hand side, right? We cannot use backward, even we cannot use backward scheme because we don't have any node on the left hand side. So you have to deal with only forward difference approximation. Okay, but the problem is that forward difference approximation is only first order accurate, right? So that is kind of suffering you are having, that for intermediate nodes you are having second order accurate scheme, but for the first order for the boundary node you have to deal with only first order accurate schemes, okay, which may affect your results. Okay, so you need to have another formulas where you can also retain the consistency of your order of accuracy. Okay, you can have a second order accurate for all the intermediate or all the boundary nodes. Okay, so that is what something which we will talk about in now. Okay, so this is just an overall idea that you can have some schemes based on simple formulation, but there are some problems with the obtain schemes. The next topic, normally I discuss the kind of boundary condition like Dirichlet boundary condition. Then you can have a Newman boundary condition. You can have a mixed boundary condition. Okay, and then I normally discuss the kind of PDE, right? Why we need to understand the nature of PDE, right? But before doing that, let us try to get the formula which are more higher order accurate. Okay, right. So it's 3 p.m. So right. So I think we are on the right track. Hmm. Okay. So now let us try to derive some formula for higher order approximation. Okay. So now let us start with only second order accurate, but in the meanwhile I will also uh, boil down to first order accurate schemes. Okay. That okay, so we'll derive lots of formulation, and I will just give you some basics idea that how will you get this kind of formulation, right? Because deriving for each and every term might not be possible in this limited time. Okay, so let us talk about forward difference approximation. For example, this is our domain. Okay, so I'm just recalling what we have studied so far, and we will utilize that particular formulation for the upcoming thing. Okay, so let's suppose this is our one dimensional domain. This is node I, this is I plus 1, this is I plus 2, and you have I minus 1, I minus 2. And let's start with approach 1, which is kind of forward approximation. Okay, so just wait. Yeah, so we are actually interested to have a formulation for second order accurate, second order differential term. So let us take an example of del square phi by del x square, right? So one of the formulation which is second order accurate, we have already defined. Okay, we have actually defined only one formulation for second order derivative, and that is nothing but central difference approximation, right? Now can we have another formulation, like for example I want to retain only forward difference approximation? Can I get more accuracy with forward difference, or you can say one-sided approach? Yes or no? That we will study in a in a next duration. Okay. Right. So let me define d square phi by dx square with forward difference approach. Right. So forward difference, that means obviously I'll be taking more node on this particular side. Okay. If I talk about backward scheme, then I'll be taking nodes on the backward side. Right. So now I can de- express this particular term as a d by dx of d phi by dx. And if I call this d phi by dx as some function f, then I can say that this is my d phi by, df by dx, which is a kind of first order accurate. Okay. And now I want to write or express this particular term with forward difference approximation. Okay. And I am talking about this particular function at any node I. Okay. So that's why I'll take this particular node at I. Okay, again here also I'll write I means nothing but I'm talking about the second order differentiation is at this particular node I. Okay, right. So how can I write this particular df by dx in terms of forward difference approximation? Can you help me? What should I write over here? This is f of at which term, at which part? I plus 1 minus f of I divided by delta x, correct? So this is our forward difference approximation which we have seen. We have already derived this approximation, right? So whenever you are writing forward difference approximation, you are taking this node and immediate right hand side node. Okay, so that's why you can write df by dx, that is equal to f at I plus 1 minus f at I divided by delta x, where delta x is actually distance between these two nodes, right? But we know that f is nothing but d phi by dx. Okay, so we'll try to substitute this particular term. So I can say that this particular term, which is actually d square phi by dx square at any node I, that is equal to, so instead of f of I plus 1, I will write d phi by dx at any node I plus 1. Okay, this I plus 1 is something, so that's I have to put I plus 1 over here. Similarly, f at any node I can be written as d phi by dx at I. Okay, and then you have this delta x in the denominator, which is already there, right? Now I hope everything is clear. Okay, so what we did so far, we have expressed this d square phi by dx square in terms of d by dx into d phi by dx. Then in order to just for the sake of simplicity, we have considered this d phi by dx as a some variable f, so that you can write this particular term as df by dx. Now I want to have an expression with forward difference approximation. Okay, so that's why I have expressed df by dx at any node I, that is equal to f of I plus 1 minus f of I divided by delta x. But I know that f is nothing but d phi by dx, so I'll have just substituted d phi by dx instead of f. Okay, so I'll have this particular term, that is d phi by dx at I plus 1 minus d phi by dx at I divided by delta x, right? Now if you carefully see this equation, then this is also first order accurate. This is also first order, sorry, not first order accurate, but this is also first order differential term, right? So here also I can use the forward difference approximation. Okay, so that's why this d phi by dx at I plus 1 can be written as, what should I write over here? Can you help me? Right, so again let me draw up this figure. So this is my node I, this is I plus 1, this is I plus 2, this is I minus 1, this is I minus 2. Now I want to write d phi by dx at this particular position and with forward difference approximation. That's why I will consider this node as well as the node which is in the immediate right hand side position. Okay, so that's why d phi by dx at I plus 1 can be expressed as phi at I plus 2 minus 5 at I plus 1 divided by delta x, right? And similarly, if I want to express this d phi by dx at I, I'm talking about this particular term. Okay, So I'm talking, I want to derive d phi by dx at this particular position, and I want to use forward difference approximation. So that's why I will use this node as well as the node which is exactly at the right hand side, right? So that particular expression, I mean, this d phi by dx at I can be written as 5 at I plus 1 minus 5 at I divided by delta x, right? So I have just replaced this particular two term with this formulation, but I also have this delta x in the denominator, right? So that is what I am writing over here. So this is also delta x. So finally, if I simplify this equation, then my d square phi by dx square at any I can be written as phi I plus 2 minus this phi I plus 1 and this phi I plus 1 will be clubbed together. So you'll have a 2 phi I plus 1, and then this minus and this minus becomes plus phi I divided by delta x square, right? So this is your formula of d square phi by dx square with forward difference approximation. Okay, so now what is the important things you will understood is that in order to define this d square phi by dx square at I with forward difference approximation, you need to have a information at I, then I plus 1 and I plus 2, right? So you are actually involving two neighboring node in order to get this particular formulation. Okay, and same way you can also define d square phi by dx square with backward approximation. Okay, so let us try to understand that also. So d square phi by dx square at any node I with backward difference approximation, right? So how will you do that? Again, you will follow the same philosophy that just define this particular term as d by dx into d phi by dx. Okay, and then express this d phi by dx as a some function f. So you have a df by dx at any node I, right? But here we are interested in backward difference approximation, right? So if I draw this particular domain, then this is I, this is I plus 1, this is I minus 1. Okay, so I know that in backward difference scheme I can write d phi by dx at any node I is equal to f of f at this particular node I minus f at I minus 1 divided by delta x. So f of I minus f of I minus 1 divided by delta x, right? But we also know that f is nothing but d phi by dx, correct? So I can rewrite this expression as d square phi by dx square, which is nothing but this particular term. Okay, that is equal to d phi by dx at I minus d phi by dx at this particular point, that is I minus 1, and whole divided by delta x. Okay, so uh, right, so this is going on. Now what we will do, we will express this d phi by dx at I with backward difference approximation. Similarly, d phi by dx at I minus 1 with backward difference approximation. Okay, so I'm just directly putting that value. Okay, because we now since we have repeated this particular steps many times, so I hope now you are able to write without even looking at this figure, right? So d phi by dx at any node I with backward difference approximation is phi I minus phi I minus 1 divided by delta x. Similarly, this particular expression is sorry, this is actually phi at I minus 1 minus phi at I minus 2, right? Then delta x, and this whole will be divided by this delta x. Okay, so if I rewrite all these things, then my final formulation will be like phi I minus 2 times phi I minus 1 plus phi I minus 2 divided by delta x square. Okay, and that this is an expression for d square phi by dx square for any node I. Okay, so if I see on in a picture, then actually In order to derive this d square phi by dx square at any node I took the help of node which is available at I minus 1 and I minus 2. Okay, so that's why this backward as well as forward difference schemes are called one-sided scheme, right? Because we are taking the help of all the nodes which are available on single side of the node I, right? And for node, we have already expressed, this central difference approximation for d square phi by dx square, and for that, what we did, we actually, added equation one and equation two, right? But you can also follow the same strategy, and you can derive the same equation. Okay, so that particular approach, let us try to, understand for the sake of completeness. Okay, so for that, okay, so let me again, remind you what we are doing so far. Okay, so we are actually trying to express or derive the expression of d square phi by dx square with forward difference approximation. That was actually approach 1. Then we use backward difference approximation. That was actually approach 2. So this was our approach 2, where we use backward difference approximation. And now we will use central difference approximation. That is actually approach 3. And for that we will use central difference approximation. Okay, so I hope now you will be able to write in your pen and paper. Okay, I mean, you are mixed kind of participants we are having. So for some people that is kind of things which you might have studied in your UG or PG level, but based on my interaction with many people, whether they are faculty from NITs or some students, PhD students or MTech students, there are many participants which are not aware of these things, or if they know, then they haven't used all these things for their project or some assignments, right? So they are not able to derive. Okay, because every year we used to have BTech students for final year project, and when I ask them to derive everything something like this, then they are not able to do that. Okay, so with that understanding in my mind, I'll try to explain everything from from the scratch. Okay, so whenever you comes across any such differential term, you have some confidence that you will be able to express each of these derivatives in terms of finite differences. Okay, so that's why I'm putting this thing on chalk and talk things. Anyway, so I want to express this d square phi by dx square at any node I with central difference approximation. So again, I'll do the same thing. That is, let us call this particular term as d by dx of d phi by dx, and that is called this as of f. Then you have this df by dx at any node I. Okay, now if you recall the central difference approximation, then you have this node I, you have node I plus 1, you have node I minus 1. Then your final formulation was, this can be expressed as a f at I plus 1 minus f at I minus 1 divided by 2 delta x. Okay, because distance between I plus 1 and I minus 1 is nothing but 2 delta x. So this was the formulation which we have studied, right? Right. That you can do, or what you can do. I mean, if you go with this particular formulation, right? For example, you have started with backward difference approximation and you have derived this equation. Here, in order to define this fi, it is not compulsion that you go with backward difference approximation only. Okay. For example, you have defined this equation, right? Now, in order to define this fi, we have again used backward difference approximation. Okay, which was nothing but this particular formulation. Okay, that is backward. Here also we have used backward difference approximation. Okay, but it is not compulsory that you start with backward and go ahead with backward. Here also you can use other scheme and derive the expression. Okay, um, yeah. For example, let us go with this one only. Okay, let us remove this part and go ahead with the previous formulation only. Okay, so that you can have a mixed feeling that sometimes we have this confusion that initially we have expressed in terms of backward, then why we are again using backward? Can we have a flexibility of again using forward or not? Okay, so that kind of confusion should be there. Okay, so let us try to understand that part. Okay, so what I am writing, that I am again defining the d square phi by dx square as a df by dx, where f is nothing but my df by dx. Okay, and for this I want to use backward difference approximation, so I'll say that this is my fi minus 1 divided by delta x. So this I have derived using backward difference approximation. Right, now I can rewrite this as a d phi by dx at I minus d phi by dx at I minus 1 whole divided by delta x. Okay, so this is the same thing. Instead of f, I have written df by dx at that particular node. Okay. Now, in our previous approach, we have again expressed this d phi by dx using backward difference approximation. But let's suppose I don't want to use backward difference. I want to go with forward difference approximation. Then what should be my formulation? Okay. So with forward difference approximation, I can write or express this d phi by dx as 5 at I plus 1 minus 5 at I divided by delta x. Correct? Similarly, forward difference approximation for this particular node is phi at I minus phi at I minus 1 divided by delta x, and obviously whole things will be divided by delta x. Okay, so if I explain or simplify this particular term, then I'll get phi I plus 1 minus 2 times phi I plus 5I minus 1 divided by delta x square, and this is the expression of d square phi by dx square at any point I. Okay, now one surprising point that is to be noted is that we started with backward difference approximation. Okay, let me remove this part. Okay, so we have started this expression with backward difference approximation. Meanwhile, we also introduced forward difference approximation for the intermediate term, and then we got this particular formulation. Okay, now if you compare this equation with the same equation which we derived for by adding equation 1 and equation 2. Okay, let me go back to that particular equation. Okay, so if I go back to this equation, this was my formulation, right? So so this is nothing but 5 at I plus 1 minus 2 times 5I plus 5, sorry, 5I minus 1 divided by delta x square. Okay, so if you add these two equations, then also you will get the formulation, and here also you are getting the similar kind of formulation. It is 5I plus 1 minus 2 5I plus 5I minus 1 divided by delta x square. Okay, now here while deriving this expression, you have combined backward and forward approximation, and because of that you are getting contribution from I plus 1 as well as I minus 1. Okay, so on figure I can say that this is my I, this is my I plus 1, I minus 1. Okay, so I wanted to express d square phi by dx square at this particular node I. So I took the help of both the neighboring node which are available on both the sides. So this formulation which we derived just now is actually central difference approximation. Okay, and based on our previous investigation, we know that this approximation is actually first order equivalent. Okay, so in my initial maybe initial 15 minutes, I have derived expression of df by dx with forward, backward, and central difference approximation. And at this particular point of time, I have derived expression of d square phi by dx square with forward, backward, and central difference approximation. Okay, right. So now, if you analyze again in a similar fashion, that this is our domain. This is node I. This is node I plus 1, I plus 2, I minus 1, I minus 2. Okay, so if I recollect what we have derived so far, so d square phi by dx square at any node I with forward difference approximation, I got this expression, that is phi I. Uh, Let me check what was the equation. Yeah, this was the equation, right? So phi I plus 2 minus 2 of phi I plus 1 plus phi I. Okay, so that is what I am writing, but I'll start with phi I only. Okay, so phi I minus 2 phi I plus 1 plus phi I plus 2 divided by delta x square. So this was expression which we derived. Okay, so if I mark the points which are used in this formulation, then this is I plus 1 and I plus 2. Right? This is our one-sided approach. Right, and similarly with backward difference approximation, I got d square phi by dx square at any node I as phi I minus 2 phi I minus 1 and then plus phi I minus 2 divided by delta x square. Okay, so if I mark that particular point which involved in this formulation, then this is I minus 1 and I minus 2. Okay, so again backward difference approximation is also one-sided approximation. Okay, and then with the last one, that is central difference approximation, my d square phi by dx square at any node I is actually phi I plus 1 minus 2 times phi I plus phi I minus 1 divided by delta x square. Okay, so while in this particular formulation, I need to have a knowledge of phi at node number I minus 1, I and I plus 1. Okay, so that's why this is a central difference approximation. Right, now I have already introduced some of the problem. Right, so now so far we have answered few of the questions. Right, for example, the question, if I recollect, then there are right. So I don't want to go back to that particular thing, but let us recollect what were our original question. Okay, so our question were like, we have expressed d phi by dx, that is first order derivative, with forward, backward, and central difference approximation. This was first order accurate. The second approach, that is backward difference approximation, is also first order accurate, whereas the central difference approximation is second order accurate. Right. So we have asked ourselves that is there any possibility to define d phi by dx with one-sided approach, either forward or backward, that is of second order accurate? Not only second order accurate, but it may be more than first order accurate. Okay, so that was our first question. That is something which we are looking for, right? Because we know that when we are dealing with boundary nodes, we need to have and if we want to have a second order accurate scheme, then we cannot use either forward or backward difference approximation. And central difference approximation for boundary nodes has its own limitation, right? Because of non availability of the boundary nodes, we cannot use central difference approximation, right? So we need to have a something with one sided approach which is also second order accurate. Okay, so this was the one question which we have to answer. And second question was like, we have at that particular time we have seen t square phi by dx square with central difference approximation, and that equation was derived by adding equation 1 plus equation 2. And at that time we asked ourselves that can we have a d square phi by dx square expression with forward difference approximation or backward difference approximation? Then we have just answered this question that yes, you can have forward and backward difference approximation with d square phi by dx square. Okay, and central is already there, right? So now let us try to derive the expression of d phi by dx, which is more than first order accurate, right? So that we can handle the boundary nodes, very smartly. Okay, so it's 3:30. Already been 5 hours. So I'll just take a 2 minutes of break just to drink a water, okay, and just to calm down. But I'll be starting in a short time. Okay, so within a 1 or 2 minutes, I'll be again continuing.
Okay, sir.
Yeah. Okay. Anyway, let us start. Okay. So yes, I hope this everything is visible, right? Okay, so now we want to have a second order accurate scheme for the first order derivatives like df by dx, right? So that we can handle this boundary nodes very smartly. So that if you have a something like Newman boundary condition where you are applying some heat flux or something like that, then you don't have to suffer, right? So one thing is for sure that if you consider any or one-sided approximation, that like for example this is our nodes I plus 1 and I minus 1, right? So in order to define this d phi by dx at any node I, so with forward difference approximation we have considered only two nodes, right? One is at I and one is at I plus 1. Similarly for d phi by dx with backward difference approximation we have also considered only two nodes. One is at I and one is at I minus 1, right? Now if I want to still stick to my one-sided approach, that might be forward or backward, but I want to have a more accurate scheme, then what I have to do, I have to introduce more neighboring nodes, right? For example, if I want to work out with forward difference approximation, then what I'll do, I'll take the help of just wait. Yeah. So this is I plus 2. So I'll take the help of not only I plus 1, but I will also take the help of I plus 2. And then I'll try to get a scheme which is second order accurate. Okay. In order to get third order accurate scheme, then I'll take another node into the picture. Okay. So by introducing more and more neighboring node, you can have a more order, the more order accurate scheme. But the problem is that you have to pay penalty, right, by adding more and more number of grid points. Okay, so that is what you have to understand, right? So now how will I decide whether how many nodes I have to consider? Okay, I mean that actually depends on whether you are working with one-sided approach or central difference, right? Or you can say two-sided approach. Okay, so for that general thumb rule, you can summarize it is as follows. So let's suppose P is order of derivatives, and let's suppose Q is something which is called order of accuracy, order of accuracy of the approximation, right? Then you can define or you can decide the number of nodes using this formula, right? So for one-sided approach, right? One-sided means either forward or backward. You can write n that is equal to p plus q. Okay, I'll revisit whether it is matching or satisfying with our general understanding which we derived so far, right? And right, so this is with one-sided formula which is order of okay, let me remove this part. Okay, and then you can, if you are working with second order, or sorry, for central difference approach, central difference is nothing but two-sided approach, right? So in that case you can say that your number of nodes is actually p plus q minus 1. Okay, let us try to revisit whether it is matching with our whatever exercise we have done so far, right? For example, let me have a first order derivative which is d phi by dx. Okay, and I want to have a first order accurate scheme. I don't know why instead of O I am using this delta symbol, but uh, so order of delta x, that is for this particular formulation, your uh, you know uh, this order of derivative is actually 1, right? That means p is equal to 1. You are looking for order of accuracy that is also equal to 1, so q is equal to 1. Okay, and you are using one sided approach, then your n is actually p plus q, that is equal to 2, right? That is exactly matching with what we did so far, right? For example, you have these three nodes I plus 1 and I minus 1, and I want to express this d phi by dx with forward approximation. Then this is nothing but phi at I plus 1 minus phi at I divided by delta x. We need only two nodes, I plus 1 and I minus 1. Similarly, I can use backward difference approximation, so I will have a phi I minus phi I minus 1 divided by delta x. Right, so I took help of only two nodes. One is this and one is this one. Right, but when it comes to central difference approximation, right, so we know that this is order of accuracy of 1. Then this backward difference approximation, that is also has a order of accuracy of 1. But if I use central difference approximation, then my equation was phi at I plus 1 minus phi at I minus 1, right? On the both side of I have to consider. And then you have this delta x term. Oh, sorry, 2 delta x term, right? Now I know that this is second order accurate, correct? So for this particular formulation, my p, that is order of derivative, is 1. And for this particular formulation, my q is equal to 2. Okay. And I know that for central difference approximation, number of nodes required to express this particular formulation is p plus q minus 1. Okay, which I have just written over here. this equation. For central difference approach, n is equal to p plus q minus 1. Okay, so if I substitute the value, then this is 1, q is 2, and here is 1. So you will left with two nodes, right? And that two nodes we have actually used, phi at I plus 1 and phi at I minus 1. So this is just an interpretation of the formulation. Okay, so now let's suppose if I ask you that you write an expression of second order derivative d square phi by dx square with an accuracy of, let's suppose, delta x. Okay, and you can use any of one-sided approach. Then now you can easily see that for this particular equation your p is equal to 2, here your q is equal to 1, right? So n is equal to p plus q because we are talking about one-sided approach. So you need at least three nodes to express this particular formulation, right? And that is what we have already defined, a few minutes ago, right? Similarly, you can also, let's suppose I am now interested in d cube phi by dx cube, okay, with and let's suppose order of accuracy, let's suppose delta x square, and you want to have either forward or backward difference approximation. Then here your p is equal to 3, here your q is equal to 2, right? So again you can say that n is equal to p plus q, that is equal to 5, isn't it? So now at this particular point you have some idea that how many nodes you actually need to consider. Okay, so let us continue with this approximation only. Okay, so with this formulation you have clear cut understanding that you need at least 5 nodes, and you also know that you are talking about forward difference approximation. So in addition to node I, we will also consider 4 additional nodes which are on the right hand side of that particular I, right? So this is what I am talking about. So let's suppose this is node I. Then with forward difference approximation, you have to consider I plus 1, I plus 2, I plus 3, and I plus 4. Right? So that's why you have 1, 2, 3, 4, and 5 nodes which you have calculated. Right? So you can, in a rough manner, you can write an approximate formula for d cube phi by dx cube, which is nothing but our, this particular term, right? So you can, in a general way, you can say that my expected formulation could be something like this. That is d cube phi by dx cube, that is equal to phi I, but I don't know whether it has a plus sign, negative sign, it has some other coefficients involved with each or not, right? So that's why I'll, in a general way, I can write this is actually a phi I plus b phi I plus 1 plus c phi I plus 2 plus d phi I plus 3 plus e phi I plus 4. Okay, I mean, uh, I have to arrange this one. Okay, so I have to somewhere adjust this thing. So this is I plus 4 and whole divided by delta x cube, right? Because it has to be consistent with this dx cube, right? And here if I go back to this particular term, then I know that order of accuracy of this expression should be delta x square. So all the leading edge term which we are neglecting has a coefficient of delta x square, right? So now the question comes is that, yes, you have some general idea that how your final formulation should be, but what are the values of a b c d and e? How can you derive all this equation, right? How will you derive all this coefficient? So that is something you should know. Okay, now I am not explaining that particular methodology with this complicated thing, but let us start with very simple expression which is a kind of first order accurate. So if you understand how you can derive ABC with that formulation, then you can extend that knowledge with all the higher order schemes. Okay, so now here I want to explain the methodology with which you can calculate all these derivatives that appears in your governing equation. Okay, so let us start with very simple, first order derivative term. So again, let us state that we have this particular formulation which is d phi by dx. Okay, and we want to have an order of accuracy which is delta x square. Okay, and we want to retain this accuracy with forward difference approximation. So this is one of the question which I am answering. Okay, we have listed down some of the question, and this is one of the answer of those question. Okay, so for example, if you recall, for first order derivative we had three scheme. One is forward, one is backward, one is center. But we know that with forward and backward we are having order of accuracy only one. That is order of accuracy is delta x. Here we want to express or derive an expression for d phi by dx which is second order accurate and which also forward or you can say one sided. Okay, so for that, how many nodes I required? So for that you can again recall the same formula that here your p is equal to 1, q is equal to 2, and since this is a one sided approach, your n is equal to p plus q, that is equal to 3, right? So one thing is for sure that you need at least 3 nodes. Okay, and this is a forward difference approximation, so you need I plus 1 and I plus 2, correct? So I can, in a rough way or in a generalized way, I can write an expression that d phi by dx at any node I, that is equal to a into phi I plus b into phi I plus 1 plus c into phi I plus 2 whole divided by delta x, and this is the second order accurate, right? Because we have just mentioned over here. So all the leading or you can say higher order terms has accuracy of delta x square. Now our task is to calculate the value of a, b, and c. How will we get all these values, right? So this is what we are understand now. Okay, so this equation I can rearrange as follows. Okay, so rearranging this particular term, I can say that my equation becomes a into phi I plus b into phi I plus 1 plus c into phi I plus 2. Okay, that is equal to d phi by dx at any node I into delta x, right? So what I'm doing now, I'm just taking this delta x to the left hand side, and this particular term I can also take on the left hand side. Okay, so that's why uh, I have this particular term which is initially it has a order of accuracy of delta x square, but this delta x will also multiply by with it, so you have a order of accuracy of delta x cube. Okay, so this is a simple way of writing the expression. Okay, we have just rearranged this particular equation, nothing else. Now this particular right hand side term I can also express as follows. Okay, so I can divide this equation into two parts. I mean it is, I'm not dividing, it is actually there only. So let me call this particular term as left hand side because it is left hand side, and this is a right hand side term. Now this RHS term I can write as follows, that is d phi by dx at I, okay, which is already there. It is multiplied by with delta x. Then I can also take this d square phi by dx square, right, at node I. But this kind of term it is not there actually. So I'll multiply this term with 0. Okay, so this is actually 0. Then I'll take this particular term, which is the order of accuracy of delta x cube. Okay, so this is actually not a 0, but this is order of accuracy. Okay, so this is just a slight modification on right hand side term. Okay, and we will try to get similar term on the left hand side, and then we will try to have a one-on-one comparison between left hand side term and right hand side term. Okay, now in the left hand side term I have this particular formulation. One is phi I plus 1 and other one is phi I plus 2. Okay, so let us try to express that particular terms using forward difference approximation. Okay, so with forward difference approximation, I can express phi I plus 1, that is equal to, right, so phi I plus 1 is nothing but phi at x plus delta x. Okay, so in that particular term I can say that phi I plus delta x into d phi by dx at I plus delta x square by 2 factorial, then d square phi by dx square at I plus delta x cube by 3 factorial, d cube phi by dx cube at I, and so on. Okay, so we don't have to write each and every term. And similarly, this was only first term, right? Phi I plus 1. But similarly, we also have a phi I plus 2. So with, again, with forward difference approximation, you can express phi I plus 2 as follows. So this phi at I plus 2 is nothing but phi at x plus 2 delta x. Okay. So that's why with Taylor series expansion, you can say that this is actually equal to phi I plus 2 delta x with obviously d phi by dx at node I plus, here again you have a 2 delta x whole square, so I can say that this is actually 4 delta x square divided by 2 factorial, then d square phi by dx square at any node I plus delta x cube, right? So I mean, here actually delta x is, our delta x is actually 2 delta x, right? So it becomes 8 delta x cube by 3 factorial d cube phi by dx cube at I n plus some higher term. Okay. So what we will do now, we will substitute this value and this value in this equation. Okay. So this phi I plus 1, whatever terms we are having on A, this will be multiplied by with B, and similarly the terms with phi I plus 2 will be multiplied by with C. Okay. So we will just simply, substituting this expression with the, derived expression. Okay. So my left hand side term, it will becomes something like this. Okay, so my left hand side term, that is a phi I will remain as it is, right? Now I'll replace the terms which are associated with phi I plus 1. Okay, so all those terms will be multiplied by with b, right? So whenever you see any terms which is having a, coefficient b, that means they are actually, coming from expression of phi I plus 1. Okay, so that's why you have a b phi I plus b delta x into d phi by dx at I plus b delta x square by 2 factorial, then d square phi by dx square at I, then plus b delta x cube by 3 factorial, then d cube phi by dx cube at I. Okay, and then you can have a other terms with phi I plus 2. So all the terms which are multiplied by with c, those are actually terms related to I plus 2. Okay, so that is what I am writing. So c phi I plus 2c delta x into d square phi by dx square at I plus 4c delta x square by 2 factorial, then d square phi by dx square at I plus 8c delta x cube by 3 factorial d cube phi by dx cube at I, and some other terms. Okay, so this is actually my left hand side term. And similarly, the terms which I have, written on the right hand side, that I am straightly, substituting. Right. So my right hand side term was, but before writing that, let me collect the terms which are common. Okay. So if I see the terms which are associated with phi I, then this is one of the terms. So A, then this B will be also clubbed together. And then here also we have a term that is called C. Right. So my equation becomes A plus B plus C into phi I Okay, and then I'll try to club the terms which are associated with d phi by dx. Okay, so this is one of the term. Then you may have this particular term. No, sorry, not this one. Where is the term? Did I miss that part? It seems like I have missed the that particular term. Okay, let me check. Huh? I think yeah. So I have c phi I plus 2c delta x. Okay, so there is a mistake here. This is actually d phi by dx. Okay, and here I have a d square phi by dx square, right? So if I try to club the terms which are associated with d phi by dx, then these are the terms, right? So b delta x plus 2c delta x. So my terms is actually b plus 2c and delta x and d phi by dx at node I, right? Similarly, I'll try to club the terms which are associated with d square phi by dx square. So one of the term is over here and another one is over here. Okay. So with that, I can say that my equation becomes b plus 4c delta x square by 2 factorial then d square phi by dx square at any node I. Okay. And lastly, I'll try to club the terms which are associated with d cube phi by dx cube. Okay. So this is I'm writing over here. So your final terms which we are clubbing is actually b plus 8c delta x cube by 3 factorial and d cube phi by dx cube at any node I. So this is our left hand side term, right? That is we have just manipulated, and on the right hand side, obviously you have this particular term. So for the right hand side term, I'll use another color. So this right hand side term I am writing as it is. Okay, so this particular RHS I am writing as it is. So on the right hand side you have a d phi by dx at any node I into delta x plus 0. Okay, so this is actually 0 into delta x square into d square phi by dx square at any node I, and uh, let us create some space for the last term. And finally you have order of accuracy, which is second. This is third order, right? So this is order of accuracy. Let me check. Huh? Yeah, so this is the term which we will be having, but I think this is actually square. Okay, order of accuracy is a square. No, it was actually a square, but since we multiply that square with delta x, so that's why you have a delta x cube, right? So this was the term on the right hand side. Okay, so this was actually correct. This was 3. Right, so now I'll have a one-on-one comparison with the each and every term. Okay, so on the left hand side I have a plus b plus c into phi I, but I cannot see any terms on the right hand side which is having a phi I term. Okay, so with that I can conclude that a plus b plus c is equal to 0. Okay, so what I'm doing, I'm just comparing left hand side term and right hand side term. So with that I can say that a plus b plus c is equal to 0 because I don't have any term on the right hand side which has a phi I term only. Okay, so what we are doing, we are actually comparing only these two terms. Right, so we are actually comparing these two terms, left hand side and right hand side. Right, so now a plus b plus c is equal to 0. As you can see that there is no term of phi I on the right hand side. Now if I compare this particular term, which is having d phi by dx, then b plus 2c is equal to 1, right? Because we have some terms, identical term on the right hand side. So b plus 2c, that is equal to 1, right? And similarly, if I see the third term, Then here I have a b plus 4c with you know second order derivative of d square 5 by dx square. But here I have put that term with 0 as a coefficient, right? So I can say that b plus 4c is equal to 0. Okay. Now we have three equations and three unknowns. So we can solve this particular equations and you will get the coefficients are as follows. So A you will get as a minus 3 by 2, B is equal to 2, C is equal to minus 1 by 2. Okay. So now you have final formulation of this d5 by dx, which is a second order accurate forward difference approximation, right? So if you rewrite that expression, then this is something which we wrote. Okay. So d5 by dx at any node I was actually a phi I plus b phi I plus 1 plus c phi I plus 2 divided by delta x, which has the order of accuracy of delta x square. Okay, so this was the formulation which we wrote initially, and we were intended to find out the coefficients a, b, and c during this whole exercise. Okay, so now if I substitute the values, then I'll get minus 3 by 2 phi I plus 2 phi I plus 1 minus 1 by 2 phi I plus 2 divided by delta x. Okay, and if I simplify this equation, then my final formulation will be like minus 3 phi I plus 4 I phi plus 1 minus phi I plus 2 divided by 2 delta x. And I know that this formulation has the order of accuracy of delta x square. Okay. Uh, right. So order of accuracy is delta x square. Here also delta x square. Okay. So now with this exercise, we understood how to derive expression of one-sided scheme that is with second order accurate, but still which is having first order. So this particular expression has a first order derivative and second order accuracy. Okay, so this is how you can also derive a similar expression with backward scheme as well as other scheme. Okay, so I'm just writing the value if you go with the backward scheme. Okay, I'm not, again there is no point of deriving the similar thing, right? Because the overall idea is just to give you some feeling that how you can derive all this expression. Okay, so this expression was with forward difference approximation, but with backward difference approximation or backward difference approach, you can also get the similar equation. So that is d phi by dx at any node I, that is equal to 3 phi I minus 4 phi I minus 1 plus phi I minus 2 divided by 2 delta x, and this scheme is also second order accurate, right? And other second order accurate scheme we already know, and that scheme is nothing but center difference scheme. Okay, that we have already derived. Okay, that is, I'm just writing for the sake of completeness only. So we also know this in the approximation. So d phi by dx at I is equal to phi I plus 1 minus phi I minus 1 divided by 2 delta x, which is a second order accurate. Right. So we initially we have derived this expression, but we put a constraint of this equation that this equation you cannot use for the boundary nodes, right? Because you need one node on the forward direction and one node on the backward direction. But if you have a forward and backward difference approximation, which are also second order accurate, then you can handle this boundary condition very smartly, right? So these are the three formulas which you can maintain the second order consistency, right? For example, central difference approximation you can use for the central node, and either forward or backward difference approximation you can use for the boundary nodes, and you can maintain the second order accuracy. Okay, right. So now I'm just noting down other formula for second order, differential. Sorry, second order differential term. Okay, so I mean, it is up to you whether you are, if you are interested, you just try to get all these, coefficients, and otherwise, if something is handy to you, then you can straight away put that equation and derive the formula, or you can continue with your code. Okay. So for the sake of completeness, what I am writing now is, formulation for d square phi by dx square, and that is second order accurate. Second order accurate. Okay. So one formula we have already derived, that is with central difference approximation. Okay, but if you are working with either forward or backward difference approximation, then first of all you need to understand how many nodes are required. Okay, so I'm just writing down the final equation. So this d square phi by dx square at any node I can be written as phi I minus 1 plus 2 phi I plus phi I plus 1 divided by delta x square, and obviously order of accuracy is delta x square, right? So this equation we have seen, and similarly you can also use one-sided approach, like for example forward difference approximation, and you can get this equation, that is 2 phi I minus phi and phi I plus 1 and plus 4 phi I plus 2, okay, minus phi I plus 3 divided by delta x square, and obviously this has the order of accuracy delta x square. And similarly with backward difference approximation, you can have this formula, that is d square phi by dx square at any node I, that is equal to 2 phi I minus phi phi I minus 1, then plus 4 phi I minus 2, and minus phi I minus 3 whole divided by delta x square, and with an accuracy of delta x square. Correct. So this is just for the sake of completeness, right? So that you have certain things in your hand, so that whenever you try to derive this expression, you can compare your final results with the given equation. Okay. Now, for the sake of illustration, you can also have a fourth order accurate central difference scheme. Okay. So I'm just writing. You can also derive the similar expression. So d square phi by dx square at any node I, which is a fourth order accurate. So symbol is order of accuracy is delta x to the power 4, right? And the third immediate question is that what scheme you are talking about, right? So with let's suppose central difference approximation. So if you use these three approximation, then first of all you need to understand that how many nodes are required, right? So again here you are using p is equal to 2, q is equal to 4, and since this is a central difference approximation, number of node is equal to p plus q minus 1. Okay, so that's why you will require 5 nodes just to have this formulation. Okay, so your final equation I am just writing, so this is actually your d square phi by dx square, that is equal to minus phi I plus 2 plus 16 phi I plus 1 minus 30 phi I plus 16 phi I minus 1 and minus phi I minus 2, and the whole things will be divided by 12. I think delta x square should be there. Okay, I think why it is not there, I'll just check out, but it should be there. And then this is having order of accuracy of delta x to the power uh, should be 4, right? Right. Okay. So this is an expression of d square phi by dx square with. So now you can see that there are how many nodes? One, two, three, four, and five nodes, right? And this is the central difference. So you have two nodes on the left hand side and two nodes on the right hand side. Okay. So similarly, you can also derive any kind of expression with any order of accuracy. Okay. But one important point which you have to remember is that while deriving all this expression, we have assumed that we have a uniform grid mesh. Okay, that means delta x is constant for all the nodes. But when it comes to non-uniform needs, you have to, it is kind of headache you may have. Okay, so for that you need to have a separate exercise. Okay, right. So now the exercise for d square phi by dx square is we have already seen, but you can also implement this understanding for d square phi by dy square. Okay, so only thing is that instead of I plus 1, you have a jth coordinate, right? So that is j plus 1, j minus 1, something like that. But when it comes to mixed derivatives, right, for example, you will have this particular term that is called del square phi by del x del y, right? Then how would you treat this particular derivative? Okay, so these mixed derivatives are also one kind of headache we have, right? So whenever these terms are appearing in this equation, then we have to be careful. Okay, so let us try to derive some fundamental approximation for similar terms. Okay, so now we'll be focusing on del square phi by del x del y. So this particular formulation can be written as del by del x of del phi by del y, correct? And if I want to use, let's suppose, central difference approximation, which is a second order accurate, right? So I can say that this is my some function f, right? So I and j, node ij, right? So what I'm talking about, so this can be written as del f by del x at I and j, and I'm talking about central difference approximation. Central difference approximation. Okay, so for first order derivative, your central difference approximation is actually f at I plus 1 comma j minus f at I minus 1 comma j, and that will be divided by 2 delta x, right? Because this is something which we have already seen, right? So my equation is del f by del x at any I j, that is equal to this particular term. Now, if I, again substitute what is f, then my equation is, it is like del square phi by del x del y, that is equal to, instead of f, I am putting del f y by del y at I plus 1 comma j minus del f by del y I minus 1 comma j divided by 2 delta x. Okay, so I have just substituted, del f by del y instead of f. So let us try to understand all this thing in a grid, spacing. So let's suppose we have this many kind of grids. Okay, and let's suppose this is a some node I, this is some node j. So obviously, sorry, this is j. Okay, and this is I. This is I and this is j. So this is obviously I plus 1, I minus 1, j plus 1, j minus 1, and at present I am talking about this del square phi by del x del y at this particular point. So I need to define this del phi by del y at I plus 1 comma j. I plus 1 comma j is nothing but at this particular point. Okay, so I want to define this del phi by del y at this particular node. So again, if I use central difference approximation, then I can write this del f by del y at I plus 1 comma j is nothing but phi at I plus 1 j plus 1 minus phi at this particular point. Okay, so I'll take the help of these particular two nodes and then I define this del phi by del y. Okay, because I plus 1 is constant. Now my derivative is y. So I have to play with jth variable. And same is true with this particular formulation, right? So for this particular formulation, my I minus 1 is fixed and my derivative is y. So I have to play with jth variable. Okay, so for that particular thing, I have to use this node and this node. Okay, so let us substitute this expression one by one. So on the left hand side again, I have the same thing, that is del square phi by del x del y. Now on the right hand side, I want to express del phi by del y at I plus 1 j using these two node number. Okay, so I can simply say that phi at I plus 1 comma j plus 1, right? Because position of this particular node is I plus 1 and j plus 1, and similarly position of this node is phi I plus 1 and j minus 1, and obviously this will be divided by 2 delta y. Similarly, if I take these two nodes, then coordinate of this node is I minus 1 j plus 1, coordinate of this particular node is I minus 1 j minus 1. So my equation is phi I minus 1 j plus 1 minus phi I minus 1 j minus 1 divided by 2 delta y, right? And obviously the whole thing will be divided by 2 delta x, right? Because that was already there. This 2 delta x was already there. We have just replaced the numerator term. Okay, so I think after putting all this thing, you just have to rearrange this particular term, so you will get this expression, that is del square phi by del x del y, that is equal to phi I plus 1 comma j plus 1 minus phi I plus 1 comma j minus 1 minus phi I minus 1 and j plus 1 plus phi I minus 1 j minus 1, and the whole things will be divided by this 2 delta x and this 2 delta y. Okay, so you will be having 4 delta x delta y, 4 delta x delta y, and this particular expression has order of accuracy of delta x square delta y square, right? Why it is second order accurate? Because we have used central difference approximation, which itself second order accurate. Okay, so this is the final formulation for del square phi by del x del y, which with central difference approximation and second order accurate. Now if you carefully see this particular nodes which involve in this expression, then you would notice that this is our grid spacing, this is j, this is I. Okay, and I want to derive this del square phi by del x y del x del y at this particular location. Here if I see the position of node, then this is phi at I plus 1 j plus 1, which is nothing but this particular node. Then other one is phi I plus 1 j minus 1, which is nothing but this one. Then here you have phi I minus 1 j plus 1, which is this particular point. And then you have phi I minus 1 j minus 1, which is this particular point. Okay. So surprisingly, you are calculating del square phi by del x del y at this particular node, but there is a no contribution from that particular point. Okay, on the right hand side, you never have any term that is called phi ij. Okay, so that is the one important observation we can have, that when you are deriving del square phi by del x square with this particular scheme at any particular node ij, then all the four neighboring nodes will contribute into the final derivation, but there is no contribution from the node ij. Okay, and this might be the issue with the stability of overall iteration process. Okay, so and because of that only people are saying that this mixed derivatives are always challenging. Okay, because your iteration, or you can say your convergence, may be affected because of non-participation of this node ij. Okay, so we must have certain formulas where contribution from this node ij should be there or should arise. Okay, so this will actually improve the rate of convergence of your overall iterative process, because we normally use Gauss-Seidel method, right? Some iterative process to converge the results, right? So I'm just writing the final formulation where you can also have a contribution from this node ij. Okay, so that is I'm writing over here. I'm not explaining how we derive this thing because it will take lots of time. Okay, so I'm just writing the final formulation, and then we'll try to understand the how contribution from all the nodes comes into the picture. So that expression is something like this. So del square phi, sorry, del x del y at any node ij, that will be equal to phi I plus 1 comma j plus 1 minus phi I plus 1 comma j minus phi at I comma j plus 1. Um, then you have a plus phi I minus 1 j minus 1 minus phi I minus 1 comma j minus phi I j minus 1 plus 2 phi I comma j. Okay, so and this whole bracket will be actually divided by 2 delta x delta y, and this particular formulation is order of accuracy of delta x square delta y square. Okay, so now if you carefully see how many nodes are participating in this formulation, then let us first try to draw the grid size. Okay, uh, yeah, so let's suppose we take almost 5 grid size. Okay, so I may not be able to draw the straight line, but let us try to do that. So 1, 2, 3, 4, and 5. And similarly here we will have 1, 2, 3, 4, and 5. Okay, and let us give some name to all these lines. So this is ij. So obviously I plus 1, I plus 2, I minus 1, I minus 2, and j plus 1, j plus 2, j minus 1, and j minus 2. Okay, so we are at present talking about this particular node. So let us see how many nodes are contributing in the final formulation. Okay, so if I start with this particular term on the right hand side, so I have a I plus 1 j plus 1. So I plus 1 j plus 1 is nothing but this particular term. Okay, then the second term is I plus 1 comma j. So I plus 1 comma j is this particular term. Then you have a I and j plus 1. So I is this one, j plus 1 is this term. Then fourth one is I minus 1, j minus 1. Okay, so I minus 1, j minus 1 is nothing but this one. Then I minus 1 comma j, which is nothing but this particular term. And then you have a I comma j minus 1. So you have a I, and this is a j minus 1. Okay, and we are talking about del square phi by del x square, sorry, del x del y at this particular node. So if I highlight this particular contribution, then I would notice that these are the nodes which are participating in the final formulation. Okay, and if I see the relative weightage, okay, or you can say the coefficient associated with all these terms, then that I can write as, so if you see this phi I plus 1 j plus 1, then it is having plus 1 coefficient, right? So this is having plus 1. Then you have a I plus 1 comma j, it is having minus 1. So I plus 1 comma j is having minus 1. Okay, and similarly I am straight away writing all these things because it is already there in the equation. Okay, so here you will have a minus 1, here also you have a minus 1, here you have a plus 1, and here you will have a plus 2. Okay, so if you diagonally see, then you would notice that this is plus, sorry, this is plus, this is plus, and this is also plus, whereas others are negative. Okay, so this is a contribution from the neighboring nodes, and you can also have another formula. So this formula is you have expressed with one of the schemes which we have discussed, but you can also have another expression which I am writing over here. Okay, so another expression where you can also have a contribution from the node ij. Okay, so that is what I was discussing. We derived this formula, but surprisingly there was no contribution from the central node ij. Okay, and which may affect the stability of your result, which may affect the convergence. So that's why we have written this expression where you have also contribution from the node ij. Okay, but this is not the only one equation. You can also have another formula. Okay, so that formula is almost identical. The only thing is that the position of I and j will be different. Okay, so I'm just explaining that equation in this uh, in this figure. Okay, I'm not writing that equation because it will take lots of time to write each and everything. But by looking at this figure, you can imagine what should be the formula or formula for that particular equation. So again, I'll note it down all these things. That is I j, sorry, j minus one, j minus two, j plus one, j plus two, I plus one, I plus two, I minus one, and I minus two. Okay, and I am talking about only this particular term. So uh, although I haven't written that particular expression, but the final weightage from all the nodes are, all these nodes will be participating. So one is this one, this one, this one, this one, this one, and this one. Okay, so if I highlight the contribution, then uh, this is something you would notice, which is a kind of, you can say, mirror of that previous one. Okay, in the previous case, we have a positive weightage in a diagonally upward direction with positive x and positive y, and here if I notice the relative weightage, then this is the weightage. Here you have minus 1, then plus 1, plus 1, minus 1, plus 1, plus 1, and minus 2. Okay, so here your negative weightage is in a, you can say, minus x and positive y direction, so in a diagonal direction. Okay, so the important things which we understood over here is that your node ij can also have a contribution, and which actually improve your stability, but still this particular formulation is having some issue. Okay, so if your formula in your formula, if your node at phi ij, if it is having a highest weightage, then it then your convergence becomes very very stable. Okay, then you can use your Gauss Seidel method or something like that. Okay, so you have to sometimes you have to derive similar expression. Okay, I'm not going into that particular direction because it is already 4:30. Okay, and I won't be able to cover everything, but I can just illustrate one of the example where you can have some favorable condition where the weightage of the central node is amongst the highest of all other nodes, and because of that your convergence is very very stable. Okay, and one of the example you can have is Laplacian equation, which can be written as del square phi by del x square plus del square phi by del y square is equal to 0. Right, so if I use central difference approximation for this square for second order derivative with respect to x and y, then I can express this del square phi by del x square as phi I plus 1 comma j minus 2 phi I plus phi I minus 1 comma j divided by delta x square, then plus phi I comma j plus 1. I may not be having enough space, so let me write over here. Okay, So phi I comma j plus 1 minus 2 phi I comma j plus phi I comma j minus 1 whole divided by delta y square. Okay, so for the first term we played with ith variable because the derivative was with respect to x, and for the second part we have played with the jth variable because derivative with respect to y. Okay, so obviously if you consider delta x equal to delta y, then you can actually rearrange this particular term and finally club this minus 2 phi I and minus 2 phi I j together, and then you have a minus 4 phi ij. Okay. So in a final expression, if I want to explain the relative weightage, then it will be something like this. Okay, so okay, probably these are enough to illustrate. Right. So this is I. This is let's suppose j. Then I plus one, j plus one, j minus one, I minus one. And let us try to understand the contribution from each and every node. So you have phi I plus one comma j. So it is having plus one contribution, and we are actually talking about this particular node. Okay. So I plus one comma j is nothing but this particular node, and it has a contribution of plus one. Then you have a minus 2 phi ij, which is nothing but this particular point. So minus 2 I am putting as it is. Then plus, sorry, the plus, yeah, so plus 1 at node of I minus 1 comma j. Okay, so I minus 1 comma j is nothing but this particular point, which has a contribution of plus 1. Then you have another node which is phi I comma j plus 1, which is nothing but this particular node, and it has also contribution of plus 1. Then again at node ij you have a minus 2. So here you have a minus 2. And then at I comma j plus, sorry, j minus 1 you have a contribution of plus 1. So this minus 2 and minus 2 I can club and code it as a minus 4. Okay, so now I can say that the central node at which I am deriving the second order derivative, it has the highest weightage. Okay, and this is a kind of favorable condition which we can have in order to uh, you know uh, get a faster convergence. Okay, now this is the thing which we have discussed so far that are limited to first order derivative and second order derivative, and obviously we have discussed some of the formula which we can derive for first order and second order accurate scheme. Okay. Now, uh, just wait. Huh? Yeah. Okay. Yeah. So what I was telling you that so far we have discussed various order of accuracy of schemes, but that those are limited to first order and second order scheme. Okay. But you can follow the similar approach and you can derive an expression of third order accurate with a desired order of accuracy. Okay, so I'm not going to derive all these things because I hope the overall idea behind how you can derive this expression is clear to you. But for the completeness of this particular lecture, I'll try to note it down so that you can verify. Okay, so for example, I'm just noting down the final expression. So let's suppose you are interested in del cube phi by del x cube. Okay, that particular term, if you are interested, and you want to have order of accuracy of, let's suppose, 1, then what should be the formula, right? So uh, this is a third order differential term. and you want to have order of accuracy first order, and let's suppose you want to have a forward difference scheme. Okay, so I'll leave up to you. You just practice this thing and try to get whether you are getting this equation or not. Okay, so your final equation would be like this. So this del cube phi by del x cube or dx cube at any node I would be equal to 1 over delta x cube, and then you have a phi I plus 3 minus phi I plus 2 plus I should start from the left hand. Yeah. Then 3 phi I plus 1 minus phi I. Whole thing will be divided by, sorry, we have already taken this delta x cube into consideration. Okay, so you don't have to divide separately. And obviously this particular term has the order of accuracy of delta x. So this is the terms which we are actually neglecting for hardware term. Right. So this is one of the formulation which you can have. But if you want to have a second order accurate with d cube phi by dx cube, then uh, so you have this d cube phi by dx cube with an accuracy of delta x square. Okay, and again with forward difference scheme, your expression would be something like this. So d cube phi by dx cube, that is equal to 1 over 2 delta x cube and minus 3 phi I plus 4 plus 14 phi I plus 3 minus 24 phi I plus 2, then plus 18 phi I plus 1 minus phi I. Okay, we have already taken 1 by 2 delta x cube, so you don't have to write separately, plus 21 by 12 delta x square and d to the power 5 of 5 divided by dx to the power 5, which is a kind of leading edge term which we are neglecting. Okay, so this is a formulation which has a accuracy of delta x square. Okay, now similarly you can also write an expression with backward difference scheme. Okay, so let me write all these things, okay, because we have some time and I don't want to go into other topic because it will take lots of time. Okay, so again with the same formulation, that is d cube phi by dx cube with order of accuracy of delta x square, but with backward difference scheme. Right, this kind of schemes you will use when you are handling the boundary condition. Okay, so whether you are, for example, it depends where your node is situated, whether you are on, it may be possible that you are working at neighboring node, not exactly at the node, but you are at neighboring node, but you want to have a more nodes, right? So there also you can use this scheme. So second order accurate with backward difference scheme, so your equation would be like d cube phi by dx cube at any node I, that is equal to 1 over 2 delta x cube. In bracket you will be having phi I minus 18 phi I minus 1 plus 24 phi I minus 2 minus 14 phi I minus 3 plus 3 phi I minus 4 minus 21 by 12. I think up to here your bracket will be closed, right? And then you have minus 21 by 12 delta x square and d to the power 5 of 5 by dx to the power 5. Okay, so this is a leading term edge which you are neglecting. And you can also have a second order accurate with central difference scheme. So let me write the final formulation. So again you have a d cube phi by dx cube with an order of accuracy of delta x square and now you are using central difference approximation. Okay, so with this term, your equation would be like uh, d cube phi by dx cube, that is equal to 1 over 2 delta x cube, then phi of I plus 2 minus 2 times phi I plus 1 plus 2 times phi I minus 1 minus phi I minus 2 minus 1 by 4 delta x square del to the power phi by del x to the power phi at any node I. Okay, so these are some of the formulation which I have written down over here. Okay, and the session will be recording, so obviously we will provide you the recorded version of the session so you can go through and verify whether you are getting this formulation or not. Okay, so the entire idea of conducting this particular session is that, for example, you are working with any problem where you don't want to go to, finite element or finite volume method, right? And your, scheme demands finite difference scheme or method. Then if you are having some differential term in your equation, then you should have some confidence that yes, I can at least write the equation and then I'll proceed with the coding part. Okay, so that was the overall idea of having this particular session, right? So what we have studied in this particular session, so we started with the first order derivative of df, sorry, del phi by del x. Then we derived three different schemes based on Taylor series expansion. Okay, then we also understood that the forward and backward scheme were actually first order accurate, whereas central difference scheme was second order accurate, right? And then we ask ourselves, can we improve the order of accuracy of forward and backward by any means? That particular things we have answered in this session. Then secondly, we derived an expression of second order derivative, that is d square phi by dx square, and the derived expression was second order accurate. Then we ask ourselves, can we have another schemes which are based on forward and backward difference approximation with other order of accuracy, right? And that is also we have answered in this particular session. And we also understood that with a given order of derivative, with a desired order of accuracy, and with a desired approach, whether it is one-sided or central approach, how to calculate the number of nodes which are required in the final formulations. And once you get that particular numbers, then how would you calculate the coefficients which are A, B, C, D, E, whatever the coefficients you are considering, that how will you get those coefficients. Okay, so that is also we have studied. Okay, the only thing which is left, okay, so after that we also discussed some of the uh, the terms, right? For example, if you consider some of the formulation, then you would notice that there is a no contribution from the node itself. There are neighboring node which are actually participating in the final formulation, but there was no contribution from the node itself, right? So we also express some of the formulations, right? And then we also understood that if your central node has the highest weightage, then it is actually a kind of favorable situation for our convergence things. Okay, and then we also uh, express some of the formula of d cube phi by dx cube for the desired level of accuracy. Okay, now with this I can actually end this particular session, but I still have a feeling that I haven't covered the time derivative part, right? Because if you have a term that is called del phi by del t, then three schemes actually comes in the picture. One is called implicit scheme, another is called explicit scheme, and the third one is called the central one, right? So for that, or normally we called it as the Crank-Nicolson scheme in finite volume method. Okay. Now that I won't be able to cover, because if I start that discussing, then it will again take almost 1 hour or more than that. So what I would advise you that there is a YouTube channel. You just YouTube and check Vipul Patel SVNIT, something like that, or VMP SVNIT. So you would find some of the video lectures which I recorded and uploaded during the pandemic situation, which was initial pandemic, which was at the peak, right? When we had that long lockdown, right? So just for the sake of benefit to my students, I recorded some of the video lectures and uploaded in my YouTube channel. So you just refer to those videos, right? And then just go through those video and let me know if you have some question from those video as well. Okay, then I'll try to answer those questions. Right. So it's 4:45, and I think that's all from my side. Actually, there are lots of things which I can still cover, but we have to respect because I also have to see your patience. Okay, because after some particular time, our mind our mind will not be able to accept anything. Okay, whether it is useful or not. Okay, so respecting that things, right? I'll end this particular session, and I'll open the session for question and answer. Okay, so if you have any question, then please you can ask the question. Okay, probably it seems like no one has any question. Okay, that should be fine. Actually, if you have any question, you can always email me. It is not like that. One session is over, then uh, you can't ask the question. Okay, you can ask whatever question you have in email. Also, we'll try to answer all this question. Right. Anyway, so this is the end of this particular session, and tomorrow we are meeting at 10 a.m. Okay, and tomorrow will be okay. Dr. Hemant B. Mehta, sir, who is one of the coordinator of this HTTP, he will be covering this coupled conduction radiation. Okay, so this particular topic is actually divided into two sessions. So in the first session, he will be discussing the theoretical aspect, right? Because radiative transfer equation itself is a kind of complex equation because it contains both integro. I mean, it contains integration as well as differentiation. So people called it that equation as the integral differential equation. Okay, so I'm not talking about the radiation, surface to surface radiation. Okay, I'm talking about the radiation transfer which is taking place in a participating media. Okay, for example, if sun is traveling through our earth, then our earth has a lots of moon, and we are also participating in that particular phenomena. That's why during the this rainy season you would find humidity, right? So those are the kind of practical example of participating media. Okay, so he will be discussing how you can couple. First of all, he will discuss what is the radiation heat transfer in participating media, what is the governing equations, and then how you can couple radiation with the conduction. Okay, and in the next day, at the next day, he will demonstrate through code development that how you can write a code for coupled conduction radiation problem. Okay, and so we are in contact with the Tensors people. Initially, we agreed that they will be demonstrating combustion modeling through ANSYS, but at that time we decided another date. It was actually 18th of August, but at the last time we had to shift this particular time to 17th August. So they will be confirming whether they are able to present tomorrow or not. Otherwise, we will ask one of our expert to demonstrate the combustion modeling. Okay, so that is um, not an issue. Yeah, so you people will get the recording. There is no issue. But the thing is that we had some bad experience with the recording because participants have that mindset that anyway we are going to get the recording. So what is the point of attending the session? Actually, that is not a right approach. Okay, that is just for your convenience. We are actually giving you the recording, but you have to attend all the session. Okay, I mean possible. You try to attend all the sessions as much as you can. Anyway, so we are meeting tomorrow at 10 a.m. Okay, so with this, I'll end the session. Yeah, thank you, Yogesh.